inverse square of the distance has some deep significance. Maybe gravity and electricity are different aspects of the same thing. No one has ever succeeded in making gravity and electricity different aspects of the same thing. Today, our theories of physics, the laws of physics, are a multitude of different parts and pieces that don't fit together very well. We don't understand the one exactly in terms of the other. We don't have one structure from which all is deduced. We have several pieces that don't quite fit exactly yet. And that's the reason why in these lectures, instead of having the ability to tell you what the law of physics is, I have to talk about the things that are common to the various laws, because we don't know, we don't understand the connection between them. But what's very strange is that there are certain things that are the same in both. But now let's look again at the law of electricity. The law goes inversely as the square of the distance. But the thing that is remarkable is the tremendous difference in the strength of the electrical and gravitational laws. People who want to make electricity and gravitation out of the same thing will find that electricity is so much more powerful than gravity that it's hard to believe they could both have the same origin. Now, how can I say one thing is more powerful than another? It depends upon how much charge you have and how much mass you have. I'm certainly, you can't talk about how strong gravity is by saying I take a lump of such and such a size, because you chose the size. If we try to get something that nature produces her own pure number that has nothing to do with inches or years or anything to do with our own dimensions, we can do it this way. If we take the fundamental particles, such as an electron, any different ones will give different numbers, but to get an idea of the number, take electrons. 2 electrons, a fundamental particle. It's an object. It's not something I don't have to tell you what units I measure in. It's 2 particles that are fundamental particles, and they repel each other inversely as the square of the distance due to electricity. And they attract each other inversely as the square of the distance due to gravitation. Question: what is the ratio of the gravitational force to the electrical force? And that is illustrated on the next slide. The ratio of the gravitational attraction to the electrical repulsion is given by a number with 42 digits, and goes off here. This is written very carefully out, so that's 42 digits. Now, therein lies a very deep mystery. Where could such a tremendous number come from? That means if you ever had a theory from which both of these things are to come, how could they come in such disproportion? From what equation has a solution which has, for one, 2 kinds of forces, an attraction and a repulsion, with that fantastic ratio? People have looked for such a large ratio in other places. They're looking for a large number. They hope, for example, that there's another large number. And if you want a large number, why not take the diameter of the universe to the diameter of a proton? Amazingly enough, it also is a number with 42 digits. And so an interesting proposal is made that this ratio is the same as the ratio of the size of the universe to the diameter of a proton. But the universe is expanding with time, and that would mean the gravitational constant is changing with time. And although that's a possibility, there's no evidence to indicate that it's in fact true, and there are several difficulties, partial indications that it doesn't, that the gravitational constant has not changed in that way. So this tremendous number remains a mystery. I must say, to finish about the theory of gravitation, 2 more things. One is that Einstein had to modify the laws of gravitation in accordance to his principles of relativity. The first was, one of the principles was that effects cannot occur instantaneously, while Newton's theory said that the force was instantaneous. He has to modify Newton's laws. They have very small effects, these modifications. One of them is all masses fall. Light has energy, and energy is equivalent to mass, so light should fall. And that should mean that light going near the sun is deflected. It is. And also the force of gravitation is slightly modified in his theory, so that the laws slightly change, very, very slightly, and it is just the right amount to account for the slight discrepancy that was found in the movement of Mercury. Finally, with connection to the laws of physics on a small scale, we have found that the behavior of matter on a small scale obeys laws so different, very different than things on a large scale. And so the question is, well, how does gravity look on a small scale? What is called the quantum theory of gravity? There is no quantum theory of gravity today. People have not succeeded completely in making a theory which is consistent with the uncertainty principles and the quantum mechanical principles. I'll discuss these principles in another lecture. Now, finally, you will say to me, yes, you told us what happens, but what is this gravity? Where does it come from, and what is it? Do you mean to tell me that the planet looks at the sun, sees how far it is, takes the inverse of the square of the distance, and then decides to move in accordance with that law and move? In other words, although I've stated a mathematical law, I haven't given you no clue as to the mechanism. I will discuss the possibility of doing this in the next lecture, which is the relation of mathematics to physics. But finally, in this lecture, I would like to remind, just at the end here, to emphasize some characteristics that the gravity has in common with the other laws that we have mentioned as we passed along. The first is that it's mathematical in its expression. The others are that way too. We'll discuss that next time. Second, it's not exact. Einstein had to modify it. We know it isn't quite right yet because they have to put the quantum theory in. That's the same with all our other laws. They're not exact. There's always an edge of mystery. There's always a place that we have some fiddling around to do yet. That, of course, is not a property, probably not a property. It may or may not be a property of nature, but it certainly is common with all the laws as we know them today. It may be only a lack of knowledge. But the most impressive fact is that gravity is simple. It is simple to state the principle completely and have not left any vagueness for anybody to change the ideas about. It's simple and therefore it's beautiful. It's simple in its pattern. I don't mean it's simple in its action. The motions of the various planets and the perturbations of one on another can be quite complicated to work out, or to follow how all those stars in the globular cluster move is quite beyond our ability. It's complicated in its actions, but not in the basic pattern or the system underneath the whole thing, is that's a simple thing. That's common in all our laws. They all turn out to be simple things, although complex in their actual actions. Finally comes the universality of the gravitational law, the fact that it extends over such enormous distances. That Newton, in his mind worrying about the solar system, was able to predict what would happen in an experiment of Cavendish, where Cavendish's little model of the solar system, the two balls attracting, has to be expanded 10 million times to become the solar system. And then 10 million times expanded once again, and we find the galaxies attracting each other by exactly the same law. Nature uses only the longest threads to weave her patterns, so that each small piece of her fabric reveals the organization of the entire tapestry. Thank you.